So welcome back, everyone. Today's lesson probably is going to be review of grade 9 and maybe a little bit of grade 10 as well. We're going to be reviewing quickly the exponent laws and looking at some combinations of the laws and looking at how to deal with all that. So we'll see how fast we can go through this without losing anybody. Let me know in chat if you need me to slow down or if you have any questions. And if I could just get one more yay on the audio. Okay, good. So the first law that we're going to review today, and this is starting the exponent laws and rationals unit, is the product law, which we've actually already seen a little bit of when we were doing the exponentials section. But we're just going to go in a little bit more depth today with this. So the law states that if you have two bases that are the same, so we've got a to the power of m times a to the power of n, that you can actually group those two together to give you one base with one exponent. And what we're doing to the two exponents is we're adding them together. Now, one big misconception that a lot of students will have with this is that, oh, we're multiplying and now we're adding. And that's not what's happening. Okay, the addition of the exponents is technically a trick to just speed things up a little bit. This is still a multiplication, all right? And to maybe explain that in a little bit more detail, if we look at this example here where I have 2 to the power of 3 times 2 to the power of 4, what I like my students to do is to actually break this down in their head into a whole bunch of multiplications. So how many 2's are multiplying when we have 2 to the power of 3? We have 3 2's multiplying. And then that's multiplying by how many 2's multiplying for 2 to the power of 4? Well, that's 4 2's multiplying. So what I like my students to be able to do is to look at a situation like this and ask themselves how many 2's are multiplying overall. Instead of using the trick to have a deeper understanding of what's happening, can you break it up in your head as all of these multiplications and see that there are therefore 7 2's multiplying altogether? And that's all an exponent is, right? It's just a representation of how many multiplications of a certain thing there are. So if you can do that in your head, you have a better understanding of what's happening. Now, what that can lead to is situations like the following. When you look at something like this, what I'm hoping you're going to do is you're going to say everything is multiplying, first of all. There's no additions and subtractions, so we don't have to worry about the nature of addition and subtraction here. Everything is multiplying. What are all the rules that come into play with multiplication? Well, one of the main rules of multiplication is commutativity, which means you can move all of these things around into any order. 3 times 2 is the exact same answer as 2 times 3. And that works with multiplication in this case as well. This a to the 3 at the beginning here, it actually doesn't want to be next to the b. It wants to be next to the other a. So if we wrote this the long way, we'd have a to the 3 times a to the 2, still multiplying b to the 4 times b to the 2. We're regrouping everything so that they're together. Now, this is not grouping like terms, because terms are separated by addition and subtraction. This is commutativity. It's moving the multiplication around so that all of your common bases are together through that property of multiplication. So now we can just say, well, how many a's are there and how many b's are there? I'm just going to get rid of this window here. And you can skip the step that I just wrote and definitely just go directly to the final answer, which would be, can you see how many a's are there in total multiplying? Well, there's 5 a's multiplying in total. And how many b's are there in total multiplying? There's 6 b's in total multiplying. And when you have multiple multiplications, they turn into powers. So the trick of adding the powers, yes, that works. And sometimes it's actually necessary, but if you can have a deeper understanding of what's going on here, I think you'll understand exponents a little bit better just in general. So that's the product law of exponents. Are there any questions about that? Seeing no urgent questions pop up in chat, we're just going to keep going. So let's look at the quotient rule, or the division rule. So before we get to the division rule, I just want to do a little bit of a side note here. When you have a bunch of things multiplying top of a fraction and bottom of a fraction, I wrote in red here off to the side, any top number can simplify with any bottom number. And this will come into play a little later on, but I just want to refresh your memory about this. So this 3, even though it's written above the 8, is technically also above the 9. You can rearrange these in any order you want. We just talked about commutativity. So I could write this as 4 times 3 at the top. If I wanted to, I could write this as 9 times 8 at the bottom, which means that that 3 and that 9 are one on top of the other, and that 4 and that 8 are one on top of the other. And because that's the case, you can actually simplify both of these by dividing by 3. And you can simplify both of these by dividing by 4. Okay? And if you do that, it makes your simplification a lot quicker because you don't have to multiply 3 times 4, 8 times 9, and then try to find a lowest common factor to divide by. You can just do it before you start, and what you would end up with for the 3 here would become a 1. The 9 would become a 3, because you're dividing both of them by 3. And then the 4 and the 8, well, the 8 would become a 2, and the 4 would become a 1. And then you're just multiplying those new numbers to find your final answer. Well, our final answer would be therefore 1 times 1, which is 1, and 2 times 3, which is 6. So it's like pre-simplifying the fractions. Any top number with any bottom number, any top factor with any bottom factor can simplify. So that's just a side note for some of the stuff we're going to be seeing. I just wanted to talk about it first. So here's the rule in general for the quotient rule or the division rule for exponents. And you've probably seen it like this. This was usually discussed in grade 9 and 10. So a to the m divided by a to the n is equal to a to the m minus n. But again, I've come into, and I'll show you an example of what I mean in a minute, but I've come into situations where students misunderstand this and think that a division is suddenly becoming a subtraction. That is not what's happening. We're using a subtraction of our powers as a simplification or a speeding up technique of what is actually going on. So in this case, I actually wrote out the long way ahead of time here just to speed things up a little bit. What does x to the 4 divided by x to the 2 mean? Well, it means there's 4 x's multiplying at the top and 2 x's multiplying at the bottom. And just as I showed above, as soon as you have a bunch of things multiplying at the top and a bunch of things multiplying at the bottom, any top thing can cancel out with any bottom thing. Now, x divided by x leaves a 1 behind. X divided by x leaves a 1 behind. And what we're left with is x to the power of 2. So again, what I'm hoping is when you see x to the 4 divided by x to the 2, that in your mind, you're saying there are 2 x's at the bottom multiplying, there are 4 x's at the top multiplying. How many will cancel out? 2 of the x's at the bottom will cancel out with 2 of the x's at the top, leaving 2 x's at the top behind. So I'll show you an example of what I meant by some of the misconceptions that students will have. If I give a question like 12 y to the 8 divided by 4 y to the 3, I have seen students mistakenly tell me that the answer to this would be 8y to the power of 5. They'll usually get the power right because they'll follow the rule. You subtract the exponents, 8 minus 3 is 5. But this is the problem. And I've seen it many times throughout my years of teaching. The student who does this thinks that a division all of a sudden became a subtraction and subtracted 12 minus 4, which is not the case. This is not a subtraction, this is a division. We are subtracting the powers to make our lives easier when we're combining the exponents, but it's still a division overall. So the correct answer would be, and I'll just write it over here, 12 divided by 4, which is 3y to the 5. Okay? So please don't be this person. All right? It's an easy mistake to make because, like I said, I've seen it over and over and over in my years of teaching. You're using a trick to make your life faster, but you have to understand how that trick is working to be able to use it. And I think this is what I meant by having a deeper understanding at the beginning of the lesson today. And I'm not sure if a teacher's already gone through all of this with you before, but it's important to see it again because we haven't seen exponents in a little while. The exponent laws, I should say. So understand what's happening. This is a division. There's 3 y's at the bottom, canceling out with 3 of the y's at the top. Therefore, there are 5 y's left. 12 is divided by 4. What is that answer? Okay, I think that's enough talking about that. I'll just pause for a second here if there's any burning questions in chat. Okay, seeing no questions popping up, let's take a look at this one. So this is going to combine not every law that we just saw, but a few of the situations from the laws we've just seen. This is a division. And the first thing I want you to notice is that you have A, B's, and C's at the top, and you also have A, B's, and C's at the bottom. They are not written in the same order. The bottom C, B, and A, I mixed up just to prove a point, okay? What does this A want to combine with? Well, it wants to combine with this A. And even though they're not one on top of the other, they actually are, because you can rewrite the bottom in any order you want. So that A to the 5 is being divided by that A to the 3. So often when I see a situation like this, folks, I'll immediately just write A, B, and C, because I know those are my 3 bases. Those aren't going to change. The bases don't change. It's just the powers that change. How many A's do I have at the top? Well, if I have 5 of them at the top and I have 3 of them at the bottom, 3 of them are going to cancel out with 3 of them, leaving how many behind? And yes, I know you can just do 5 minus 3, okay? But it's that level of understanding that they're canceling out that I'm trying to really entrench in your mind here. So it would be 2 A's left at the top. When we look at our B's, coincidentally, they are one on top of the other, okay? Well, we've got B to the 4 divided by B to the 5. Now, here's an interesting discussion, because we have a smaller amount of B's at the top than we do at the bottom. If you just use the rule, you would do 4 minus 5, which would be negative 1. Now, we've seen recently that a negative exponent, I am going to be reviewing that again today. I believe I get to that point today. We know what a negative exponent does. But even if you didn't know what a negative exponent does, where would the leftover be here? If you have 4 B's at the top and 5 B's at the bottom, would the leftover B be at the top or the bottom? 4 of them are canceling out with 4 of them. The leftover would be down here. That's right. We see that it's going to be at the bottom if you truly understand what's going on here. Okay? So this B to the negative 1 technically should be at the bottom of the fraction. Now, I'm going to leave it as a b to the negative 1 for now, because we're going to get back to that in a minute. But I want you to start to see that kind of thing. Now, for our c's, we've got 3 of them at the top. We've got 2 of them at the bottom. We're going to have 1 of them left. It is your choice whether you want to write a power of 1 or not. Okay? But just know that if there is a letter there, there is a power there. Okay? It's not a power of 0. It's a power of 1 because there's a c left over. All right? So we'll come back to this. Okay? And I don't know if you've done, some of you may have done complex simplifications of exponents like this before. Usually not in grade 9 though, but I'm not sure if your teachers would have pushed you to that point. But I'm hoping that it makes sense with the rules that you already have seen about exponent laws. All right, this is going to lead me to powers of 0. So what does 3 to the power of 0 equal? And I will ask chat to give me the answer here. As many people as possible answer what is 3 to the 0 equal to. You got it. Not 0, which is a very common mistake. 3 to the 0 is 1. Now, why? Why is 3 to the 0, 1? Now, let me move. Sorry, my scrolling is messing up here. Let me move. Oh. Okay, let's try this again. I want to move this out of the way, if I can. Why is 3 to the 0 equal to 1? Well, I want you to understand, and again, maybe you've seen this before, maybe you haven't. Where does a power of 0 come from? A power of 0 has to come from something. And there's only one law that we've seen so far that could potentially give us a power of 0 out of other numbers. And it isn't the law of multiplication. Because there's no way, when you multiply 2 bases, that you could get a power of 0 when you're adding 2 numbers, unless one of the numbers is negative, okay? But one of the numbers being negative, we're going to see in a minute, is going to be a division. So technically, the only way that you can get a power of 0 is if you're using, that's right, the quotient law, okay? If you look at 3 to the 2 divided by 3 to the 2, if we use the quotient law, we get 3 to the, and I'm going to write it out the long way, 3 to the 2 minus 2, and that's the only way to get a 3 to the 0. Okay? However, there is another path that we could follow here. What is 3 to the 2? 3 to the 2 is just 9. So technically, this is just 9 divided by 9, and you can technically see this just with the 3 to the 2. If you're dividing a number by itself, what does the answer always have to be? The answer always has to be 1. How many times does 9 go into 9? How many times does 3 to the 2 go into 3 to the 2? It goes in once. We just got 2 different answers from the same starting point. And in math, there is a rule that says let me write it down here. If A equals B and A equals C, that means that B has to equal C. If 3 to the 2 over 3 to the 2 equals 3 to the 0, but 3 to the 2 over 3 to the 2 also equals 1, that means that 3 to the 0 has to equal 1. So in our case, we've now basically, it's not technically a proof because we used numbers to do it, but it's a logical proof, okay? If we get one answer one way and another answer the other way from the same starting point, that means that the 2 final answers have to equal each other. And when you see a power of 0, what I'd like you to, as a deeper understanding of what's happening, remember that a power of 0 means a division of two things that have the exact same base and the exact same power. And if you're dividing two things that are exactly the same, they have to give you 1. So if you see something that looks like this example, as soon as the power of 0 is on the outside of anything, it doesn't matter how complex is in the base, sorry. Okay, you could have all kinds of additions, subtractions. It doesn't matter what's in the bracket. If everything is to the power of 0, that means we had a situation like above where we had two things that were exactly the same dividing each other, and the answer is going to be 1. Now, what happens if you have a power of 0 in the middle of a scenario like the one I've written just here? Now, I have seen some students say, oh, there's a power of 0, therefore the answer is going to be 1. No, take a step back and ask yourself what's going on here. The only thing that has a power of 0 here is the A. Powers are attached directly to the base that's next to them, okay? Unless there's a bracket around the whole thing. So in this case, the only thing that would become 1 is the A to the 0. So this is equal to 1. All right? But the rest of it is still there. So our final answer, if I write it out the long way, would be 2 times 1 times b to the 3, which would just be 2 times b to the 3. Okay? So be careful where the power of 0 is. If the power of 0 is on the outside of everything, then the answer is 1. But if the power of 0 is within something, then maybe just that one thing is going to become 1. The rest is not going to change. I am going to move on at this point. I feel like this is something you probably already know. I don't know if you saw it in that much depth before, but we're going to move on. So let's tackle negative powers. What does a negative power mean? So this is going back to that question a few minutes ago where I said we'd come back to I think it was a b to the negative 1. We've already seen this in our exponentials unit. Some of you, we went through it pretty quickly though, so I don't know if you remember, but what happens is you find the reciprocal and you change the power to a positive value. Now the power is attached to the denominator, okay? You can actually write it like this if you want, okay? Because it's a power of 1 at the top. But I'm going to show you some scenarios where that might not be the case, so take that with a grain of salt. Here's the proof, the logical proof. And it goes back to that example that I showed earlier. If you have b to the 2 divided by b to the 5, and you write those out the long way, when you start canceling stuff off, and remember there's a 1 left behind every time you do that, b divided by b is 1. Your leftover b's are at the bottom, not at the top this time. Okay? So in this case, we would get 1 over b to the 3. But using a similar process that we did earlier, using the quotient law, we also get b to the 2 minus 5, which is b to the negative 3. And that means that this and this have to equal each other. It's that a equals b and b equals c, therefore b equals c scenario again. We started from the same starting point, and we ended up with 2 different answers using 2 different proven techniques. Therefore, those 2 different answers have to equal each other. So what would happen in a case like this? And I'm going to show a few examples of this one just to really make sure. I'm just going to look ahead here because I'm forgetting what my next slide is. Okay. So yeah, we're going to look at a few examples of this stuff. All right. So this is not a case where they can actually combine. This is like a final answer. All right. And usually in math, you're not supposed to have a negative exponent in your final answer, okay? So you shouldn't leave an answer with a negative power like that, all right? What flips here would be my question, because we just saw that if you have a negative exponent, that usually does the reciprocal of the fraction. But what would we take the reciprocal of here? The a to the 4 doesn't have a negative power. Only the x to the negative 2 does. So does the a to the 4 flip? Anybody know the answer to that one? So how would you mathematically, without skipping any steps, show that only the top flips but the bottom doesn't? To flip the x to the negative 2 means writing it as 1 over x to the positive 2. But all of that is still being divided by a to the 4. Okay? So yes, that's the final answer, but I'm just trying to show you why that final answer happens. We are flipping something, but we're only flipping the numerator. I like to use the word flip instead of reciprocal, okay? We're finding the reciprocal of just the numerator. That means the denominator of the original fraction is still the denominator. Now watch the, again, depth of understanding that I'd like you to have here. I can rewrite this as 1 over x squared divided by a to the 4. But how do you divide when you have a fraction involved? What's the rule to divide when you have a fraction involved? So dividing with a fraction means multiply by the reciprocal. That's right. Now, I just said that the a to the 4 doesn't flip, though. So all of a sudden, we do have to flip the a to the 4. But it's not because of the negative exponent. It's because of the nature of dividing with fractions. So 1 over x squared becomes a multiplication by 1 over a to the 4. And we end up with 1 over a to the 4, if we write it alphabetically, times x squared. Now look at what happened from the beginning. I don't know if I can show everything at the same time here. Oh, sorry, scrolling issue again. Okay, so look at where the a to the 4 is here. It's in the denominator of the fraction. Look at where the a to the 4 is here. It's still in the denominator of the fraction. Technically, the a to the 4 didn't change positions at all. The only thing that changed positions is the x to the power of negative 2, which basically flipped upside down and joined the a to the 4 at the bottom. And this is the math that shows all of that. Okay? So we did flip the x to the negative 2. Okay, this scrolling is going to drive me a little bit batty. Okay, we did flip the x to the negative 2. It became 1 over x to the 2. Then we rewrote it as a division with a fraction involved. That makes it look like the a to the 4 flipped upside down, and it does during the division, but that just makes it join back to where it was originally, which is in the denominator. Okay? So, in other words, if you have a negative power in a numerator, you slide it down to the denominator and make the power positive. And the reverse is also going to be true. If you have a negative power in the denominator, you slide it up to the top and make it a positive power. So let's look at a couple of examples like that. So we're now going to skip all of this long process here, and we're just going to go to the final thing that you need to know. Okay, so let's look at a couple of examples of this. So in this case, my x to the 2 doesn't have a negative power, so it's going to stay as a numerator. My d to the negative 3 does have a negative power. It's in the denominator. Where's it going to go? We're going to slide that up to the numerator position. I'm going to put it after the x2 though, so that it's in alphabetical order again. No, sorry, not in alphabetical order. Actually, I should have put it first. Let me move that over. So it should technically be like that. My mistake. I did arrow it in the right place. I don't know why I was thinking I had to go after. So yeah, so the d to the negative 3 has to go up next to the numerator because it's got a negative exponent. Again, I'm just going to look ahead here. I can't remember. I don't know if I want to do that one yet. We'll get to that one in a second. Let's try, wrong color. Let's try something like this. Let's say I had, and I asked you to simplify that. Okay, and there are multiple ways of doing this, but if you want to follow the order of the laws, okay, so what we would do is we would first look at, do we have anything that needs to join together at the top? No. Do we have anything that needs to join at the bottom? No. How many u's do I have overall? So following a procedure that I showed you in one of the previous examples, what I like to do is I like to write out, okay, what are all my bases? U and V don't change. Those are the bases. They stay the same. What are the powers going to be? Well, let's use the rule for quotient law. 5 minus 7, we're subtracting the exponents, is negative 2. Now be careful with this one. Negative 4 minus negative 8. Let me write that out so you can see it. When you have a minus negative, you got to go back to our integer rules here. That becomes a plus, so this will become a positive 4. It'll be negative 4 plus 8. So you still got to remember all of those rules as well. And now in the final stages, you then ask yourself, are there any negative exponents? And there is. U to the negative 2 can't stay U to the negative 2. It's going to slide down as a denominator. So the V to the 4 is going to stay as a numerator. The U is going to slide down to the bottom, and the power is going to become positive. And usually when I show students that way of doing things, I get less students making mistakes. Okay? So let's talk about the kind of mistakes that could be done. There's another way to think about this if you understand the canceling out thing that I talked to you about earlier. If I cancel out U to the 5 and U to the 7, where are the leftover U's going to be? They're going to be in the bottom. But here's the mistake I've seen students make. They say, oh, I'm going to get U to the 2 at the bottom, but because I'm subtracting 5 by 7, it's going to be U to the negative 2 at the bottom, which means it's going to flip back up to the top. And I've lost multiple hair on my head because of that kind of thinking, okay? Don't try to combine a whole bunch of things together. Use one rule and the correct one, all right? Don't combine two different rules together. Either cancel out the U to the 5 with the U to the 7 and remember that that gives you U to the 2 at the bottom, or combine the two of them together using the quotient rule, which gives you U to the negative 2 at the top, which then slides down to the bottom. Okay? So there's a couple of different ways you can deal with a situation like this, and I know some of you are able to look and see those kinds of situations. For those of you who aren't comfortable with this yet, I recommend this way. For those of you who are comfortable with those other ways of thinking, be very careful to do it right. Let's look at this guy. So for this one, looks very imposing when you first look at it, but we're just going to take it a step at a time. This is a combination of the multiplication rule and the quotient rule, okay? And we'll see if there's going to be a negative rule pop up, but we have to simplify everything before we do that. So forgetting about the bottom for a second, if we just look at the top, that 2 wants to join up with what? Well, it wants to join up with that 4. This a to the 3 wants to join up with that a to the 2. This b to the 4 wants to join up with that b to the 5. So that's what we're going to do. We're just going to join everything up, multiplying as we go. And again, I've seen this mistake done too. Students will say 2 plus 4 is 6. No, we're not adding the bases. We're adding the powers when we need to. 2 is a base, 4 is a base. We just combine them as a multiplication. There's no exponents to them, so it's 2 times 4, which is 8. I'm going to use color to show that. So the A's, which I'm going to do in green, how many A's are there at the top? Well, there's 3 of them here. There's 2 of them there. That means there are 5 A's in total. Purple for B, how many B's are there at the top? Well, there's 4 of them here. There's 5 of them here. That means there are 9 B's at the top in total. And that would be my first simplification. So I'm going to pause there for a second, let everybody digest that a little bit. So the first step when you have a larger question like this is to analyze just the top and separately analyze the bottom. Is there anything we can simplify in just the top and anything we can simplify in just the bottom? In the simplifications I just did, are there any questions about that? Okay, I'm not seeing any questions. And again, you can always ask me questions in email later. You can, refer back to some examples or whatever. So what do we do next? So next we're going to simplify with the quotient rule. So what does the 8 want to join with? Well, there's actually a number down here. It's a 1, okay? Right? There's a 1 right here. So it's just a division of 8 divided by 1, not a subtraction. A division of 8 divided by 1, which is 8. Then we have a to the 5 divided by a to the 5. Well, yes, that's a to the 0. But it's also the same thing divided by the same thing, which is just a 1. Right? So I wouldn't even normally write that in. I'm just going to put it as a ghost 1 here to show you that there's a 1 right there. Okay? And then we have b to the 9 divided by b to the 12. And again, depending on who you are, there are 2 different ways of looking at this. I'm going to show you the way I recommend for everybody so that you always get it right. But if you're a little bit stronger in math, you may already see where is the leftover b going to be. Okay? This would be b to the negative 3, because it would be b to the 9 divided by b to the 12, which is 9 minus 12 as my trick to get negative 3. Okay? But that means that that b has to slide down into the denominator and become a b to the 3. And that would be my final answer. So you should be able to see, if you're a little bit stronger, that the b to the 9 and the b to the 12 would have simplified to give you b to the 3's at the bottom, because the 9 b's at the top would cross off and there'd be 3 b's not crossed off at the bottom once you did that. So you can do that simplification if you understand it. Just don't get it wrong. Let's do the final law. I actually didn't set it up, but we do have a little bit of time here. So the final law is the power of powers law. When you have a power of powers, what do we do with the m and n? Chat? You got it. Do you understand why? And again, it's that depth of understanding that I'm going for here. What does a power of 4 mean? What does a power of 2 mean? A power of 4, if we look at the outer power first, means there are 4 of those things multiplying. And I'd like you to be able to see that. I want you to look at 3 to the 2 to the 4 and expand it in your head as 3 to the 2 times 3 to the 2 times 3 to the 2 times 3 to the 2 in a split second. And if you can do that, you're going to see that we're then just adding up all the 2's, because these are a bunch of multiplications, and we just saw that the multiplication law is adding. Okay? Yes, you can just do 2 times 4. But do you understand why you can do 2 times 4? That's what I'm trying to reinforce. So this brings up those kinds of questions. And I mean, if I really wanted to be mean, let's do that one. Technically, this is not being mean. This is being fun. Okay. Now we've got a question that pretty much summarizes every rule that we've seen today. So let's finish with this one. Biggest mistake I see students make is right here. That 3 has a power. That 3 has a power of 1. That means that the numbers inside of the brackets are also affected by that outer power. Okay? Now the way we usually show the rule, it's multiply the inner powers, right? Now be careful, this looks like distributivity, but it's not distributivity. Okay? Distributivity is used for additions and subtractions of like a whole other story. All right? This is not distributivity. It's the power law that says that all inner powers are being affected by that outer power. But the way I look at it is how many 3's are there if the whole bracket is repeating twice, which is what that outer power means. There has to be 2 3's multiplying. So that becomes 3 to the power of 2. Okay, and I can't tell you how often, because it's happened so many times I've lost count, that students will forget about that coefficient also being affected by that outer power. Normally there's no issue with the x and y. It's only that number that has an issue. So when I multiply that 2 times 2 for the x, it becomes a 4. When I multiply that 2 times 4 for the y, it becomes an 8. And then I'm going to have 4x and y. Again, just writing out all of the bases, and now let's affect the powers. Okay, so again, that outer power is going to multiply all of the inner powers. So the power next to the 4 here is a 1 right now. So that's going to become a 4 to the negative 2. X negative 5 times negative 2 is positive 10. And 6 times negative 2 is negative 12. This, by the way, is one of those examples I kind of hinted at the fact that sometimes you have to use the trick. Okay, there is a longer way to deal with this. Second bracket here with the negative 2 exponent, but this is really, in my opinion, the most efficient way. Let's just use the power rule to bring in all of the to bring in that outer power to all of the inner powers. We'll deal with the negative exponents and all that stuff at the very end. Okay, now I still have a bunch of stuff to do at the top here before I can join it with the bottom. So to save a little bit of time, let's just put the ditto marks at the bottom. That's not an 11, okay? Those are just the repetition marks to say that the bottom is staying the same, okay? So let's deal with the top now. Let's simplify the top a little bit more. So 3 to the 2 can't join with 4 to the negative 2 yet, because I can't join a base of 3 and a base of 4 if they have exponents. All right? And I can't multiply 4 to the negative 2 times 3 to the 2. I can do 3 to the 2 is 9, though. That I can do. Okay? But the 4 to the negative 2, I'm just going to place right next to that 9 for now. Some of you already know what's going to happen to it, but I'm just going to place it next to that 9 for now. X to the 4 wants to join with x to the 10. How many x's do I have in total? I have 14 of them. Y to the 8 wants to join with y to the negative 12. Now, this is one of those cases where I have to use the trick. I have to add 8 plus negative 12, which is negative 4, right? I think I did that right. Now, I'm going to put in the 2x to the 5, y to the negative 7, because I'm going to be using it next. And you'll notice that I try to keep all of my bases in lined up together in the similar columns. Sorry. So all my x's are together, all my y's are together here. All my numbers are together. Okay. Well, let's deal with this 4 to the negative 2 now. Where is that 4 to the negative 2 going to go? It's a negative exponent. What did I just show you happens to negative exponents in numerators? Well, they slide down to the denominator. So that 4 is going to come down here, become a power of positive 2, and it's going to do that in front of the 2 that's already there. Okay, the 2 at the bottom doesn't switch positions because it has a positive 1 exponent. Okay, so the 2 just stays there. But the 4 to the negative 2 slides down in front of that 2. And now I'm just going to join my x's and y's together. So how many x's do I have? Well, I have 14 at the top, canceling out by 5 at the bottom. 14 minus 5 is 9. And then I have negative 4 minus negative 7. So if we do that off to the side, what does that give? That gives 3. So what's interesting here is even though I had negative powers with my y's, when I join my y's together, those negative powers disappear and my y just stays at the top now. And the final step would be to join the 4 to the 2 with the 2. (16) is 4 to the 2. 16 times 2 is 32. And that would be the final answer, if I didn't make any mistakes. I feel like everything was okay. It looks right? Okay, thank you. And we're going to finish the lesson there for today. All right, so as a summary, we reviewed, that's what you got as well? Okay, thank you. As a summary, we looked at the multiplication law, which the trick is to add the exponents when the bases are the same. The quotient law, which means subtract the exponents when the bases are the same. Powers of 0, which give 1. Negative powers, which are reciprocals, and powers of powers, which is multiply the inner power by the outer power. Okay? Just to maybe hint at some of the stuff we're going to eventually see. This is a hint at something that's coming soon. Could you simplify that? And technically speaking, some of you would know how to do this based on some of the work we did with logarithms recently and the exponent laws that we just saw. And I like to use the idea here of an oyster and a pearl. Yes, I have silly little math tricks to help me remember things, okay? So the idea here is you can't touch the pearl until you've cracked open the oyster. So how do we get rid of all those root symbols using the laws that we've just seen and the law of roots? We'll get there, okay? So I am going to say goodbye for the recording. I'll stay streaming for just a couple of minutes, but that's it for the recording. We will see you tomorrow for the recording.